So this is a talk about p-adic theory for local systems, but the motivation for this project comes from geometry. So let me just start with like a motivation, geometric motivation. So in my talk, p is a prime number, and then capital K is just finite extension of QP. And as usual, like OK denotes ring of integers. And then pi k is a uniformizer, and I want to denote residue field by small k. And then as a motivation, let me just consider an elliptic curve over k. So let's say E is an elliptic curve. So if you just take the minimal wire stress equation, then you can just consider reduction mod pi. Then so there are three types depending on how bad singularity you have. So it can be just still elliptic curve, or you may have a node singularity. So something that looks like this. Yes. Oh, sorry, minimal wire stress equation. So let's avoid like a 2 and 3 case, but suppose. Sorry. Your curve is defined in this way, then you just consider replace A and B so that the.
Characteristic is not 2?
Yeah, I mean it's motivation. So let's go easier situation.
Do you have another question?
Yes. But anyway, so in my talk, I mean, this case is called good reduction case. And then the first two cases will be referred to semistable reduction case. And then in this setting, there are two basic facts about elliptic curves. One is, so first, I mean, you may have bad reduction like additive reduction over k. But if you just extend the scalar, at some point, you get semistable reduction. So the first fact in this business is at least after finite extension of the space field, elliptic curve admits semistable reduction. So this is the kind of best possible like mild singularity. Another thing is, so you just ask a question whether like a curve acquires a good reduction after some finite extension of scalar, namely whether E is a potential good reduction. In this situation, you can judge this question based on J invariant. So namely, so E has potentially good reduction. Namely, it acquires a good reduction after some finite extension k, if and only if you consider the J invariant, then this is a p-adic integer. Or in other words, if you just consider a p-adic valuation, this is bounded by 1. So these are the two facts about elliptic curves over local field. And then as a motivation of my work, let me just give two remarks related to these two facts. The first thing is, so the first fact is generalized to a conjecture called semistable reduction conjecture. Namely, if you start with any like smooth projective or smooth proper variety over k, we expect after finite extension it acquires semistable reduction. So every smooth proper algebraic variety over k admits semistable reduction over some finite extension. For this talk, you don't need to really understand what this means. But roughly speaking, this means there exists a proper model over OL, and eta locally looks like you start with like several variables, and then divided by sum of them minus uniformizer of my base field L. With like, this is a general definition of semistable reduction. So this is a big conjecture about kind of like a degeneration of families of varieties over this ring of integers. And it is known for curves and abelian varieties, but I think it's open in general. And maybe I want to make a remark that you can just consider similar conjecture or like statement if you replace this p-adic field by Laurent series field over C. In that situation, it's known. And also in practice, we have a weaker version of a theorem, which is called alteration by Duyon. But still, I think this geometric question is interesting, and I think it's open in general. And another remark is related to the second fact. Namely, so let's consider a family of elliptic curves. So suppose you have a family of elliptic curve over some smooth variety. And you just consider k-valued points. And you want to just consider the collection k-valued points which your fiber has potentially good reduction. Then that can be captured by this kind of condition that J invariant or p-adic value of J invariant is bounded by 1. So in that case, so if you just consider the subset of k-valued point such that the fiber has a potentially good reduction. For simplicity, let's go k, and then the same for k bar. Then this initially is a subset of k-valued point. But if you just equip like sk by classical or like naive p-adic topology, then this inequality says this gives an analytic open subset. So namely, like having like potentially good reduction is kind of like analytic open condition in this context. So these are the two remarks related to elliptic curves over a local field. And then goal of this talk is kind of establish analog or generalization of these remarks in terms of p-adic Cauchy theory for local systems. And then so for this, maybe I'll have to explain what p-adic Cauchy theory is in the next section. And then I will just state the main result. OK. So by p-adic Cauchy theory, I want to just say the study of p-adic representation of Galois group of K, especially to try to study representation coming from geometry. So let me just introduce my notation. So Galois of K is absolute Galois group of K. And now let's consider some p-adic Galois representation. So maybe V is like finite dimensional QP vector space. So by Galois representation, I just mean continuous homomorphism from this absolute Galois group to automorphism group of V. So that's continuous homomorphism. And then maybe I need to start with giving you some examples of Galois representations. And then in general, it's hard to get p-adic Galois representations. And typically what we want to do is first get examples from geometry. And maybe you can just use deformation theory to get more examples. And for this talk, let's just focus on geometric examples. So the first example is the basic one. So if you start with elliptic curve over K, and then you can just consider p-adic Tate module. If you really prefer, you can just page change. So this means you just consider p-power torsion points of E and then consider the inverse limit. And then since the Galois group acts on the coordinates over K bar, then this is a two-dimensional p-adic representation. And then you can just do more general thing. Namely, if you start with algebraic variety, maybe for simplicity, let's say smooth and proper. Then you can take étale cohomology of this object. Maybe this is my simplified notation. So you just base change your variety to K bar, and then taking QP coefficient étale cohomology. And by functionality of étale cohomology, you get Galois action. And it turns out this is a finite dimensional QP vector space with continuous action. So these are kind of like ways to get examples of Galois representation. If you prefer, then you can consider deformation, and you get more examples. But at this point, I want to just pause and then ask a question. Namely, so if you just look at these geometric examples of Galois representation, you can ask whether these are kind of general examples or form like a very specific class of representations. And then so this is kind of beginning of p-adic theory, and then it turns out they are very special. So more precisely, so Fontaine introduced some hierarchy. So there's some like adjectives for representations. First one is crystalline, which is the smallest, and this is contained in so-called semistable representations. And then so a slightly larger class is called Rham representation. And this is inside general representations. And the key important theorem in p-adic theory is if you just look at those representations coming from geometry, they are always Rham. And then there is a huge difference between Rham representations and general representations. And then moreover, reflecting the reduction type of your variety, I mean, that also falls in smaller classes called crystalline or semistable. So let me just write this as a theorem by various people. So so étale cohomology as Galois representation is always Rham. And moreover, this falls into smaller classes if X has nice reduction type. So it is crystalline if X has a reduction over K. And then the name suggests it becomes semistable. It admits semistable reduction over K if X has good or semistable reduction. And at this point, of course, you may want to know the definition of these classes. And I just want to say this is very technical. So I just can't explain in my talk. But maybe for later purpose, I want to just give you a very unfriendly flavor of the definition. So note, definition is very technical. But the point here is Fontaine constructed so-called paired rings, which are typically denoted by B Cris, or B semistable, or B Rham. So these are QP algebra equipped with Galois action. And if, for example, if you want to define a class of Rham representations, what you want to do is starting from QP representation as here, and then you just consider extension scalar of this representation to be Rham. So you get some semilinear representation. And then taking Galois invariant with respect to diagonal action. And then V is called Rham. So it turns out this is a capital K vector space. And then the definition is if this vector space has a maximum possible dimension, namely is equal to the dimension of the original representation. And essentially, you can just give similar definition. And at this point, let me just go back to this semistable reduction conjecture. The conjecture says, every smooth propagative variety acquires semistable reduction. And if you just compare this conjecture and this theorem, then you may just try to ask, what's the difference between Rham representations and semistable representations? And then a theorem called p-adic monodromy theorem says exactly what your expectation is true. Namely, every Rham representation becomes semistable after restricted in the Galois representation, Galois group to something of finite index. This is a big theorem by Belger. So let me write the theorem. So we can just say every Rham representation is potentially semistable. So by which I mean, so there exists a finite extension such that this representation, regarded as a Galois representation of L, is semistable. And then in some sense, this theorem gives kind of p-adic or theoretic evidence that semistable reduction conjecture is reasonable. And then the goal of my talk is try to understand this theorem for families. And then so that I can also get some result, something like consequence of a second. So let me just move on to p-adic theory for local systems, and let me just write down the statement. By the way, do you have any questions so far? Mean which one?
Is that, is the expectation that it is if and only if? That means
This theorem, or?
No, I'm stupid. I'm sorry. That's a conjecture. Sorry.
Okay, so what we want to consider is want to understand a family of Galois representations. Are parameterized by a variety. Maybe for simplicity, say smooth algebraic variety. S over K. And then if you already know this kind of context, you can guess I want to just work on local systems over S. But maybe I want to just insert one quick example coming from elliptic curve so that I can connect my talk with the introduction or motivation. So naive example is, as before, if you start with a family of elliptic curve, then naively, you just consider a rational Tate module of each like special fiber, and then this admits a, I forgot my notation. For each point small s inside S, you just consider fiber, which is elliptic curve, and if you just consider it's like Tate module, then this admits action of Galois group of the residue field of S. So naively, I want to just call this as a family of Galois representation obtained as Tate module parameterized by S. And then more generally, we have a nice language to explain this situation. So in general, work on et al. QP local system. Maybe my symbol is bold font L on S. This is like a suitable sheaf in suitable topology, and you just can talk about a stalk. So for each point S inside my variety, you just consider geometric stalk, and then this admits a action of Galois residue field as my point vary over my parameter space S. So I want to just call this as a family of Galois representations. And if you have never seen this kind of language, it's not that scary. Namely, so this kind of L corresponds to QP representation of maybe assume S is connected, et al. Fundamental group of S. And then, so this is a natural process because Galois group of K is nothing but et al. Fundamental group over the point, namely spectrum of K. And then in this setup, I want to just repeat the question which I mentioned before. Namely, like how the property of being Rham or semistable behave in this kind of family. So for simplicity, let me just give a very easy definition, which may not be very standard. So definition, say my local system L is pointwise a Rham or semistable, so on and so on. If you just consider the stalk a closed point regarding the Galois representation of the residue field, this is Rham, or semistable. In the previous sense, I briefly explained. Then I can ask analog of Belger's theorem, namely if you start with a local system, which is a pointwise Rham, then how far this local system being from pointwise semistable. Also, maybe you can just talk about whether we can just define some kind of potentially good reduction locus for L, as we did in the case of family of elliptic curves. And then in the latter example, I mentioned some like open set is analytic open. So actually, in fact, it's natural to work on analytic topology. So from now on, maybe my parameter space S, I want to just regard this as, or like S is smooth ridge direct variety. Over K. If you're not comfortable with this language, you can just start with smooth algebra variety and then consider like naive topology, as naive as you can think of, which has analytic flavor, not Zariski flavor. So in this setting, so the theorem is as follows. So suppose, assume L is a Rham, a pointwise a Rham, a ZP local system on S. Then let me just write very simplest statement, namely for every S, which is a k-rational point, there exists analytic open neighborhood of this given point S, and then finite extension. And a finite extension of the base field satisfying the following property. Namely, if you restrict a local system L to U base change to this field extension, then it's pointwise semistable. Local system restricted to this base change is pointwise semistable. And then we can say more. Namely, if the given point S, and if you just consider the Galois representation at this point, if suppose this is potentially crystalline, then we can just choose U and L so that this is pointwisely crystalline. So this, the initial Galois representation is potentially crystalline. Remember, crystalline is more like a coming corresponding to good reduction in the geometric case. Then can take U and L such that this restriction is pointwise crystalline. So this is a kind of main theorem, and which I'm going to call this p-adic monodromy theorem for Rham local systems. First of all, is the statement clear?
L is finite over K.
Yes. This is the finite extension.
Is it? So I have a question.
Sure.
You define the pointwise theorem.
Mm-hmm.
Is there any notion of theorem local system? Like, is there
Yes.
any
So
theorem or
right. So I'll go to that topic, but so based on the work of Princeton, Brennan, Schulze defined notion of Rham local systems. It turns out by the theorem by Liu and Zhu that those are equivalent. Pointwise Rham is equivalent to asking your local system being Rham in the sense of Schulze. Yes. So this is classical points, namely the points with residue field finite over my base field capital K. And then so as the direct consequence of second part, we can just say, so if you start with a pointwise Rham local system, and you just consider a collection of k-valued point for simplicity, and you just choose the locus where the stalk is potentially crystalline. So this is a subset of k-value points equipped with analytic topology, and the consequence is this is analytical. So essentially, if L is coming from a p-adic theta module of relative elliptic curve, and then this generalizes the consequence I mentioned in the motivation section.
This L for the pointwise crystalline result is not the same L that makes the. I just take an L that makes one of this fiber LS bar crystalline. It's not the same L, right?
Sorry.
So this, you have this fiber
Yes?
LS bar, which is potential.
Yeah, so the second part says if I'm at one point, it's potentially crystalline. For a near point, everything is potentially crystalline.
It wouldn't be true just with crystalline. Without the word potential.
That's a good question. I just don't know. Maybe if you know elliptic curve very well, maybe you can quickly answer. But yeah, I think my method can't say anything in that direction. I'm not sure whether this is true or not, first of all. Any other question about the statement?
In the corollary, you also assume that L was pointwise Rham?
Yes.
Yeah.
Yeah, right. If this is empty, then it's analytic open. If it's not empty, potentially crystalline implies Rham. So by result of Liu and Zhu, it's kind of essentially Rham on that connected components, I think. Yeah. I have to say.
If you have it at one point, then you
Right.
everywhere.
On that connected component. So I think it's OK, but it's better to just say L is pointwise Rham. Thank you. So maybe let me just pose one question. Namely, so this theorem is more like local nature. You can also ask whether global p-adic monodromy conjecture is true. So the question is, for given like a pointwise Rham local system on S, you can ask whether there exists some nice surjective map, global one, such that if you restrict L, my local system, to this cover, you can ask whether this becomes pointwise semistable. So apart from like very special cases, I think this kind of conjecture is completely open. And of course, I haven't specified what the nice means. But so you can just consider nice to mean several things. The very restrictive situation is S prime being some base change by the base field. And then in this case, this conjecture is null by recent work of Rowlands and Lee. And then maybe you can ask whether this is true for finite tau cover or finite cover. Or maybe weakest thing is like alteration. And then I think we don't know much about these global conjectures.
Which Lee is that?
Shijian Li.
Of course, you don't want something like just a disjoint union of analytic balls, right? You want something close to algebraic or something.
Right, or kind of global nature. I think finite et al. Finite. Well, these ones kind of more like global nature, not just union of like small like et al. Opens. Okay. Do you have any other questions? Then in the remaining 20 minutes, let me give you some ideas of the proof. And then so first what I want to use is p-adic Riemann-Hilbert functor. Introduced by Rochang Liu and then Xinwen Zhu. So let me just briefly write down the rough statement. So there exists a natural functor denoted by d-Rham from QP local systems on S to vector bundles with integrable connection. On my variety S. So namely, to S, you want to associate a vector bundle denoted by d-Rham or L, and then connection. So by connection, I mean a map from d-Rham or L to d-Rham tensor with differential form, such that this satisfies Leibniz rule. And by integrable or flat, this means nabla squared is equal to 0. And then satisfying various nice properties. First of all,
Omega 1 of S?
Sorry, thank you. That's S. So first of all, this commutes with arbitrary pullback. And then, so if you just take S to be single point, then local systems is nothing but Gauss representation. In this situation, this d-Rham functor agrees with Fontaine's d-Rham functor. When varieties point. And then thirdly, so essentially the consequence of those first two properties is, so L is pointwisely Rham, or Rham in the sense of Schulze. If and only if this vector bundle has maximum rank, namely rank of this vector bundle is the same of the rank of the initial local system. So if my S is a point, then local system, yes.
Spontaneous thing has some filtration, and this doesn't.
Yeah, so I just didn't write. So you can upgrade this to be filtered vector bundle and satisfying Griffith transversality. That's also another important feature which can be missing in complex case, but I don't need that in my talk. And I realized I forgot to give you some examples of local systems, so let me just give example here.
So is it a Rham?
Yes?
The vector bundle,
Yeah, so
not a sheaf. Why
yeah, locally free sheaf.
is that it's on one point is
Is that your question?
the point was done
So essentially, so Rham in the Schulze sense is equivalent to asking whether this d-Rham of L has maximum rank. But since, by the first property, this commutes with pullback, namely specializing to one point.
so at least the drum will be the open condition.
Yes. But because of the local constancy of rank, so 1 point Rham on each connected component implied this is Rham in the strongest possible sense. So if we start with smooth proper family of smooth proper varieties, then you can just consider a local system to be the higher direct image of the constant shift upstairs. So this is QP local system. And in this situation, the stalk is nothing but étale cohomology of the fiber at S. And then so this is Rham. So in particular, this example is an example of Rham local system. So my notation for this one is just base change, so it's just one thing. And in this situation, as you might have expect, so d-Rham L is nothing but relative Rham cohomology X over S, and the connection is the Gauss-Manning connection. So unfortunately, I forgot to say, but if you start with Gauss representation obtained as étale cohomology, corresponding Fontaine's d-Rham functor gives you just Rham cohomology by p-adic comparison theorem. And this is the relative version of this. And then somehow this geometric example gives you some insight on how to prove my main theorem. So let's suppose X and S has nice integral model, like maybe expand to like a smooth proper map between smooth formal scheme. And then so you can just also consider like finite invariance called decrease of like each étale cohomology of the fiber. Then what you know is decrease is given by crystalline cohomology of the reduction, special fiber. That means decrease can be identified over all the points S which are the same residue reduction. So this essentially tells you, in general situation, using the presence of integral connection, maybe locally, you can just trivialize your vector bundle, which is roughly saying you can just construct parallel transport between two fibers and then compare them. So that's the basic strategy for the proof. So let me write this out. So let's say L on S as in main theorem, namely pointwise Rham local system. Then theory of p-adic differential equation over p-adic tells you there is this nice analytic open neighborhood of the given point. Such that if I restrict my vector bundle with connection to this neighborhood, this is trivial. So namely, there is this restriction has full set of solutions. Heuristically, this means you can just construct parallel transport and then compare different fibers. And then if you want, you can further shrink my open U so that you can assume my U is isomorphic to rigid torus. So we can also assume U is spar of A, where A is a ring of this form. If you have never seen this, this is, sorry, I think it looks a bit stupid. So if you start with low-Rham polynomial ring with coefficients in OK, namely P1 plus minus 1 in this way. And if you just consider p-adic completion of it, then this is denoted by this kind of triangle bracket. And if you invert P, that's the function I'm writing. And then naively, this means, for example, k-value points of this object is nothing but correction and tuples of elements k such that absolute value for each component is exactly 1. So this is the kind of rigid torus. And then in this setting, what we can do is, so first of all, a local system now corresponds to Galois representation of the Galois group of A, or maybe étale fundamental group of a spec of A. And then in this context, in this setting, we can define period rings, which I call horizontal period ring. Like a BST horizontal or B-Rham horizontal. And then this corresponding representation is admissible with respect to this horizontal Rham period ring. Namely, in this case, since my initial Rham local system is horizontal over U, as a consequence, this representation is horizontal Rham. And then at this point, we need to just work on p-adic host theory for rings. I mean, extending the work for p-adic host theory for fields. Then essentially the theorem becomes the following one. Namely, if this Gauss representation of A is horizontal drawn, then if there exists a finite extension of the base field such that V restricted to Gauss representation of base change of A to L is admissible with respect to horizontal semistable ring or period ring. And then for simplicity, I don't write anything more. But if you happen to find one specialization to a point at which your representation becomes potentially crystalline, then you can just take this to be horizontally crystalline. So that corresponds to the second part of the main theorem.
This is a horizontal version of inversion. Oh, no, inversion is different.
Yes.
Yeah. Does this rely in a fundamental way on knowing the fundamental group of A explicitly, or why did you have to choose this special type of neighborhood?
So that's a good question, and I'll just get to the point. Essentially, the point here is initially I start with any smooth regional variety without fixing any nice model. And then one feature of this, open neighborhood is, so first of all, this has coordinates which are invertible. Typically, that's a good setting where you can just develop p-adic host theory. And then another thing is this is kind of like a good reduction. Namely, if we just consider reduction modulo pi, then that's connected. So essentially, I need those two properties. So essentially, what we need to prove with this theorem, and then essentially, this is very technical to prove. But essentially, we use two ingredients. And then to explain this, what I want to do is I want to try to compare this entire Gauss representation to the one restricted to the Gauss point. So namely, so let's denote by curly k so if we start with this integral version, and you just consider p-adic completion of my integral structuring. And you just invert p. Then this is a complete discrete variation field with imperfect residue field. And then in such a situation, we still have a definition of period rings. And you can just talk about whether the Gauss representation is horizontally semistable drawn. So then at this point, you can prove the theorem I wrote there by combining two results. The one thing is if this is called purity theorem. Namely, if you start with horizontally drawn representation, and if you restrict this representation to this Gauss point, and assume this is horizontally semistable already, then original representation is horizontally semistable. So kind of purity theorem. You can just judge whether your representation is horizontally semistable or not by kind of looking at generic point in suitable sense. So at this point, then essentially what you have to do is you try to prove p-adic monodromy theorem for this kind of Gauss representation curly k. And then this is done by Okubo. So let me just write his theorem, which is just exactly what I said. So Okubo tried to generalize Berger's p-adic monodromy theorem for fields which may have an imperfect residue field. And then as an application, he also get p-adic monodromy theorem for horizontal representations. Namely, so if a W is a Galois representation of this field, if this is drawn, horizontally drawn, then there exists a finite extension of the base field such that this representation restricted to the composite of this field is horizontally semistable. So first he applied this Okubo theorem to this generic fiber, and then to make it horizontally semistable, then by purity result, the initial representation, after extending the scalar, you get horizontally semistable. And then this proof of this, so first of all, I think I need to make some comments about the proof. And the first comment is it's very technical. You really have to look at the structures of period rings involved. But somehow this kind of statement has appeared in different contexts of p-adic theory. So first of all, Berger and Colmet studied a family of Galois representations in the sense that Galois representation with values in some affinoid algebra to study deformation theory. And in that context, they prove p-adic monodromy theorem using like a detailed analysis of period rings. Also, Tsuji has a preprint in which he defined crystalline local systems in the case of good reduction. And he proved if you establish Rham local system, and if you restrict it to this kind of point, if it's crystalline, he proved that's crystalline local system.
But that was actually squishes. No?
But I think he's not working on regional geometry and the scheme setting, and then I should be very careful about how we can get what I actually wanted to say. But in this way, so there are some like results by studying carefully the structures of period rings, and then I also need to just analyze these structures carefully, and then finally we get purity result. So I will stop here.